Let's go to the next set, areas and volumes. Let R be the region bounded by y equal to 0 and cosine of x, where x is between negative pi over 2 to positive pi over 2. You can plot the graph. It looks like this. It's cosine function going up and down, it's sinusoidally going up and down, but from negative pi over 2 to pi over 2, it's just positive bulge. And cosine function is an even function. So the left-hand side part and right-hand side part are actually identical. So all you have to do is consider only the right-hand side part when x is greater than 0 part, and then double it, and then you can get the area, you can get the volume, everything. Okay, let's answer the first question. Set up the integral that represents the volume of the solid obtained by volume of the solid of revolution obtained by rotating the region R with respect to the x-axis. Okay, now it makes sense. Sorry about that. And then set up the integral that represents the volume of the solid of resolution obtained by the region R with respect to the y-axis. So rotate it with respect to the vertical axis. Here, when you rotate it with respect to the vertical axis, this left-hand side really does nothing because only the right-hand part will just rotate and cover entire left-hand part as well. So you don't really have to consider this part at all. For 3.1, only consider the right-hand side and double it, and 3.2, left-hand side completely ignore, just the right-hand side. That's the way it is. Okay, let's consider the first problem. This is going to be a rotor method or a washer method or coin method, no matter what you want to call. You end up with this volume formula, pi, and then radius squared. And the radius is y-coordinate. So cosine squared, that's what you're going to get. So pi y squared, but y is cosine function. So this is integral. Have you seen this integral before? Well, this is a familiar integral. Calculating the antiderivative of this cosine squared, you can use a power reduction formula, or you may call it half angle formula, whatever you may want to call. It's basically this: cosine squared being reduced into the reduced power, second power reduced to the first power, and then you can calculate the antiderivative. Looks like, yeah, this 2 and that 2 cancel out. Alright, antiderivative of 1 is just x, and antiderivative of antiderivative of cosine is sine, and then we need this extra 2 because of this coefficient. And then plugging in pi over 2 and 0, you're going to get pi squared over 2. By the way, why do I have this 2? That's because I'm taking only the right-hand side part, 0 to pi over 2, and doubling it, rather than from here all the way over there and making the computation slightly more complicated. It's better this way. But here, I'm simply asking Mathematica to calculate this integral directly from negative pi over 2 to pi over 2. And it'll turn out pi squared over 2. This computation is correct. So it's a coin method, a rotor method, and it's not really washer method because I don't have any hole down here, but they're in the same ballpark. Next problem, we are rotating with respect to the y-axis, so this is going to be a shell method. So how do you do that? We need 2 pi r times y, 2 pi and then r, the radius is just the x-coordinate. Distance from the y-axis. So that is the shell method formula when taking the rotation with respect to the y-axis. If it is a vertical line, some further adjustment is necessary to this part, but I kept it simple. This is an exam, so I didn't really have to go through all the details, just like homework problems. So I just kept it simple. So 2 pi, all right, and then the radius is the x-coordinate. Okay, and then as far as this integral is concerned, it just really standard integration by part problem, I guess. And have you done this before? Well, we have right here, and the antiderivative turned out to be this. Remember this. It's an integration by parts. So that's what we are going to do here. That's the antiderivative excluding plus c, and it's done by integration by part, and then plugging the top pi over 2 and plugging the bottom, subtract from the other. Plugging pi over 2, then what do you get? Pi over 2 times sine of pi over 2, that's 1, so that's how you get this pi over 2. And then plug in pi over 2 over here, that's 0, so I don't have anything. And plug in 0 now, sine of 0 is 0, so that part drops out. And minus of cosine of 0, that's gonna be minus 1. Why am I having positive here? Sorry about that. Minus 1. Okay, all right. And then if you distribute 2 pi, then I get pi squared minus 2 pi. Okay, that's correct. Okay, other than the previous sign mistake, everything is okay. And then here's verification by Mathematica. Okay, all right. Everything looks good. In this kind of problem, represent the integral first and then evaluating the integral, that's the second part. In this particular case, evaluating integral wasn't too bad, but sometimes they turn out to be really hard or sometimes even impossible. Okay, we have sufficient time, so let's go to the next problem. Riemann sum problem. Find an integral that represents a cumulative limits. Okay, here we go. So this is basically a 0 times infinity type limit. 1 over n is getting really, really small, close to 0. However, this infinite sum, excuse me, this is not infinite sum. This sum is blowing up to infinity because, you see, there's so many things we are adding. And what happens is, so many things that we are adding, that is number of rectangles, numerous, and then 1 over n is actually width of the rectangle. So we have a Riemann sum. This is height, and this is width, and then adding those areas of the rectangles. Upon the limit, you get the definite integral, and then here is the typical scheme. Limit of the summation is integral from 0 to 1. As a matter of fact, this is 1n, so it's going from 0 to 1. If this is 2n, in that case, you're going to get 0 to 2. If this is something like some integer order of pi n or something, then it will be 0 to pi. It can be all kind of complicated stuff, but let's keep it simple. You see, this is exam, so let's not get too complicated. Let's keep it simple. So going from 0 to 1. And k over n is going to x. 1 over n is going to dx. And if you use these conversions, you end up with this limit. This integral, excuse me. And the integral from 0 to 1, cosine of the third power, sine to the fifth power. It's a complicated integral, but it's not impossible. You see, you can reduce it using the appropriate substitution and Pythagorean. Shall we calculate? Okay, let's calculate. Let's keep it open. We're calculating this integral. Excuse me. Okay, let's calculate the definite integral. Alright, I don't need this anymore. Definite integral. And then third power can be decomposed into second power times cosine of x dx. And this cosine of x dx is actually the derivative of sine. So this can be rewritten as d sine of x, the derivative of sine, and then sine to the fifth power, and cosine squared is by Pythagorean 1 minus sine squared. So we have sine to the fifth power, sine to the seventh power, and then this is d sine of x. So we can calculate the antiderivative with respect to sine function. 1/6 sine to the sixth power, 1/8 sine to the eighth power. Of course, you can use substitution by u equals to sine of x if you will. You can do that. Go ahead if you prefer that way. Now I have this antiderivative, so all you have to do is plug into this definite integral, plug in top, plug in bottom, subtract one from the other. Plug in 1 and sine of 1 to the sixth power, sine of 1 to the eighth power, and plug in 0. Sine of 0 is 0, so I don't really have to do anything. And then if you calculate this, it'll turn out something like this. Sine of 1 is 1 radian, and we don't have simple value, but you get approximation. And then if you ask Mathematica to calculate this limit analytically, you get, 0.227 something, exactly the same as before. And is this expression same as that expression? They'll turn out to be the same, but exactly what kind of trig identity Mathematica used to reduce into this form instead of that, I have no idea. So in that case, I'll have to check numerically, and it checks out. Okay, so much for Riemann sum problem. Actually, the first half was Riemann sum, this reduction, and after that, it is just calculation of this trig integral. That concludes this review, and if time permitting, I'll dig out some other practice set exam. I'll dig out some other exam problems and then discuss some practice tests.